Work it, make it, do it, make sense.
We're going to look at fork join and how we can improve our performance slightly with ManagedBlocker. And I just want to start off by showing a CPU graph. This is on my little Pentium i7 laptop. And you can see that I've got, it looks like I've got 8 cores. I don't really have 8 cores, I've got 4 cores. But I've got hyper-threading, so it shows it as 8 cores. And if you look at the graph, you notice that there's quite a bit of green, right? If you're colorblind, you've got a problem with these graphs. And there's a little bit of red, very little, which is not a bad thing, right? Not too much red. And but at the beginning, especially on the real cores, which is 0, 2, 4, and 6, there's a fair amount of black. And black means that we're not fully utilizing the available hardware. Now, up to now, we've been very lucky as programmers because, first of all, when I was younger, every 2 years the processor speed would double, and so the systems automatically became fast without actually doing any real work. So there's this whole thing of the Doom principle. You basically play Doom for 2 years, and by the end of the 2 years, your program is twice as fast because all the hardware is twice as fast. You don't touch any code, but your code automatically gets faster. And so that was the principle we used a lot, actually too much, when I was younger. And then this processor clock speed, of course, we reached a sort of limit there, but they do a lot of instruction level parallelism and pipelining and so on. And we get a lot of performance benefits from that. But we are reaching a limit there too. And unless you're going to buy a quantum computer with like 5 million lasers pointing at you and all sorts of cool stuff, you're going to have to deal with this at some point when you're working on larger problems. And so it's getting more towards the software having to solve these problems. So the problem here is that I'm not fully utilizing the cores, and I put in a ManagedBlocker rather than just a normal blocker, and you can see that at the beginning the CPU graphs were now much greener. There's less black, and for this was quite a large calculation. It actually completed also about 8% faster. So we got performance improvements, and we got and a better utilization of our available hardware. Now I'm going to show an example that starts very simple and gets more and more complicated as we go through. First of all, there's this algorithm that you probably have all heard by now called the Fibonacci Series, where f of 0 is 0, f of 1 is 1, and then the next number is equal to the 2 previous numbers. And so the numbers get very large. Like if you've ever heard about the Australian rabbit problem, they had the Fibonacci Series in rabbits, which was a very big problem. Now, if you implemented this as a mathematician, you might say, well, this is equivalent to that, right? So let's write it like this, and because Java doesn't have a decent tail recursion mechanism, it works out f of 0 over and over and over again. And f of 2 and 3 will just get many, many, many times. So the funny thing about this algorithm is that the computational complexity is itself a Fibonacci series. So you basically have, if f of n takes 1 second and f of n plus 1 takes 1.6 seconds, then f of n plus 2 will take 2.6 seconds. And so on. And things get very slow very quickly. Well, you can't get slow quickly. After a very small n, it gets slow. And so scarily, you'll find this algorithm actually like this described or used inside Java docs. So don't read Java docs. It's a bad idea. Now, if you did an iterative algorithm, it would look like this. You only remember the previous 2 numbers, and so you don't have to work out the numbers over and over again. And if you're working out the number on a long, you'll be able to do this in like a second, but the answer won't be correct, right? Because you overflow at about Fibonacci 80 or 70 or somewhere around the overflow. So you could use big integer, but then big integer is an immutable object. It's unmodifiable. So it makes new copies every time that you change it. So if you do an add, it's actually a linear operation according to the size of the number. So you've got a linear algorithm, 0 to n, multiplied by a linear add, gives you quadratic. And you will be able to work out relatively small numbers like this, like maybe Fibonacci of 1 million, but you won't be able to work out Fibonacci of a billion. It just gets computationally too difficult. Even a million will take a very long time. Okay, now, the third attempt is to take Dijkstra's sum of squares. So I've changed the algorithm, and the algorithm now looks like this. F of 2n minus 1 equals f of n minus 1 squared plus f of n squared. So if it's an odd number, use one variation. If it's an even number, use a different variation. And actually, the real algorithm for calculating the numbers is a logarithmic algorithm. Every time you're dividing it by 2, like a binary search. And the multiplication since Java 8 has improved significantly. It used to be order n squared, but they now have two different algorithms, either Karatsuba or Cook. Karatsuba takes your very big number and splits it into two parts, and then does some maths magic, right? Something. I don't know that stuff. And then the three-way Cook splits the number to 5 segments, and again does some more wizardry to come up with the correct multiplication. So dividing it into multiple chunks gives you the opportunity to parallelize it, but they didn't do that. It does however decrease the computational time complexity. This matters. There's a big difference between n to the power of 1585 and n to the power of 1.465. There is a big difference once the numbers start getting larger. Now, you might wonder, why don't they always use Cook? Well, the setup cost is higher. So it takes a bit of time before you start seeing a difference in performance. Now, at the moment, the big integer is still single-threaded in Java 8. It'll probably stay that way for a while, but we'll hack that a little bit later. Now, I'm going to do a bunch of demos, and the way that I do this is every time that I do one demo, I commit it, and then at the end of the talk, I push it if you remind me. Any project managers here? No project managers. Okay, well, then I won't push it, right? It just won't happen if nobody reminds me. But I'm going to implement this using big integer. Unfortunately, we don't have operator overloading in Java yet. Maybe Java 13 or something will have it. But we'll do the first one. And by the way, if I try and work out Fibonacci 1000 with this current algorithm, I did a calculation, I estimated it's going to take approximately 10 to the power of 200 years to complete. Not 200 years, 10 to the power of 200 years. So it's quite a long time. We're going to do it in like 3 milliseconds in a moment. So what we're going to do is we're going to say, first of all, int of half equals n plus 1 divided by 2. Then we're going to say big integer f naught equals f of half minus 1. And f of 1 will be f of half. And then I'm going to use, if it's an odd number, I use the one calculation. If it's an even number, I use the other calculation that you see over here. Right? So let's do that. If n percentage 2 is 1, then return f naught dot multiply with f naught dot add f1 dot multiply f1. So that's f1 squared plus f naught squared. Else, if it's even, then I have the other calculation. I need to multiply f naught by 2. How do you multiply by 2? Any guesses? Shift by 1. Very good. So I return f naught dot shift left by 1, add f1 to that, and multiply that with f1. So this gives you the same algorithm that we saw, but with big integer. Okay? And the purists amongst you might say, why doesn't he use bit masking here? It ends up being the same compiled code. So let's run this and see what comes out. Would I just check something? Yes, that's correct. Okay, good. All right, so I've got, as you see, Fibonacci 1000 is calculated in like 5 milliseconds. And then as the numbers get bigger, it takes more and more time to complete. The reason I'm outputting the GCs is just to make sure that I'm not going to that I'm not doing any full GCs in the middle of my calculation, because they tend to take a bit longer than 1 or 2 milliseconds, and they can disturb the results or skew them in a certain direction. So after running it for a while, and remember, this is Fibonacci 100 million. It's a very large number. It comes out with some result, hopefully. Hopefully still today. And come on now. I've only got 40 minutes left, so it'll be done. Okay, so it starts at 46 seconds, 46 and a half seconds. And that's not bad, considering that the other mechanism, Fibonacci 1000, would have taken 10 to the 200 years. So this is not a bad result at all. And somebody asked me before I started, what is this newsletter? It's the Java Specialist newsletter. You should subscribe to that and to the Performance Tuning newsletter too. They come out once a month, and sometimes it's interesting. Thank you. I appreciate that. So you project manage material at least. Git commit minus A, and this is demo 1. Okay. Now, that's the first demo. Now, if you run that, at the moment, everything is single-threaded. So if you run it and you look at the CPU, which we'll do once more, not to the end, but just to start, you can see if I run top, that my CPU is sitting at 100% for, what's not working? For Java, 100%. And sometimes it bumps slightly over 100% because you do have GC events happening in parallel. But most of the time, it's just around about 100% because there's only one thread actually doing the calculation. But I've got 4 cores, so I should be able to do it in parallel and get better performance that way. So let's do the second approach, which is to parallelize this algorithm a bit. The idea is we can do this with fork join, and we can say let's work out the F0 in a separate thread. Now, what we're doing is something called recursive decomposition, and the fork join framework is specifically built for that. So you can see here I'm working out f of half minus 1 in a separate, possibly a separate task. I fork it, which then might allow it to start in a separate thread. And then I work on F1, and afterwards I join with the task that I created. So let's put this into the code and see if we can make our speed 4 times faster. And so we're going to make a recursive task of big integer. Big integer, which will be the F0 task equals new recursive task. It's not an anonymous in a class. It's not an interface. It's a class, so you can't use lambdas here. And compute will say return just the code that I've got down here. So I'm moving this code up to the compute. Then I say F0 task.fork. And after I've done F1, I'm going to say F0 equals F0 task.join. Okay. So before it was running at 46 seconds. Now I would expect it to run at 4 times faster. 10, 11, 11 and a half, 12, right about there, something like that. 16. Somebody said 16. Somebody's a pessimist here. Don't be so pessimistic. This is performance. It's parallelism. Everything should be fast. Okay, so we run it again, and this time, after 16 seconds, or 12 seconds, it's going to be finished, and it's going to be much faster. And, okay, so it's GC, GC, GC. And, by the way, allocation failure is not something bad. It just means that even is full, and it wasn't able to allocate more memory. Without doing a GC. Now, if you go to the bottom, you notice that it actually took 22 seconds. So it's just right about twice as fast. It's not 4 times as fast. And when I started playing with this, I saw this and I thought, oh, maybe I'm not actually parallelizing properly. Now, we'll just make a note of this and put it into our list over here, demo 2. Okay. And I'm going to run it again, and I'm going to run it next to top. Top. Yeah, oh wait, I need to do this once more. 1 second, please. I'm going to stop this. I'm going to start it once more because I want to show you that initially running at like hundreds of percent. So that's like I'm using all eight hardware threads. And after not too long, it goes down to like 400% and down to 200%. And eventually, it's down at 100%. For the longest time, it's actually at 100%. And if you go back and you do a thread dump, you'll actually see what's going on here. You'll see that the only thread who's actually doing anything is a single thread that's main that's doing a big multiply. And the reason is that this is combining very big numbers. And towards the end, what you're really paying for is the last calculation, the last multiplication, right? And I mentioned to you that the multiply is not parallel. So we're ending up, Amdahl's law tells us we really can't optimize this much more. Okay, now commit. Before I forget, this is demo 2. And let's see demo 3. So the demo 3 is to basically hack up big integer. Now, big integer is a class that works fairly well, but it's not parallel. So what we can do is we can take multiply Tomb Cook and square Tomb Cook, and we can make this into these into parallel functions. Now, what I'm going to do is I'm going to copy and paste big integer from Java Math into my project, or actually into a different module within my project with a different license, with the GPL license. And then I'm going to set up my boot class path to point to the hacked big integer class. That's my little trick here. So let's do that. And when you say boot class path, you can say /p to prepend my hacked class to the normal boot class path. So that becomes my official big integer class. Okay, let's do that. So we're going to go and first of all, go to big integer, the class. Now I'm going to teach you a way in which you can actually program a huge number of lines of code per day. All right, let me show you. It goes like this. Control A, Control C, all right? And then go here and you press Control V. And I've just programmed like 1,000 or 2,000 lines. Brilliant. I'll get a bonus end of the year for this. And then just to make sure that I'm actually using this class, I'm going to output here a static initializer block that says using hacked big integer, just to make sure I'm actually using it. So when I run this code, I'm going to now, here where this boot class path, I'm going to say boot class path /p for prepend. So my hack is going to be the first class that they see before the official Java Math big integer. And big integer actually uses other classes as well. There's a dependency, but we don't care about that because the big integer, our big integer is going to be the first one in this boot class path. Okay, just be careful. Don't ship code like that to other people because you're going to violate license agreements. Okay, now if you run that, you'll notice that it outputs here using hacked big integer. So we're good. It's using our class. And now we're going to hack it. So that's the next part. And we're going to go to the multiply Tomb Cook. Now, when I was in school, I thought I was not too bad at mathematics until I went to university and I met some people who really are good at mathematics. And then I realized I actually don't know very much at all. And when I look at this type of algorithm, my mind just goes like, I don't know what these guys are doing. And you know what? It doesn't actually matter. I don't have to understand this stuff. All I need to do is parallelize it. So what I'm going to do is I'm going to make a multiply task. V0 task equals new multiply task with A0, comma B0. Of course, I have to construct this class. So I'm going to make an inner class here with big integer A and big integer B. And this is going to say extends recursive task of big integer, like that. And then A and B must be fields. And then I'm going to have my compute function say return A dot multiply B. Right? And I'm going to do something very similar for the square task, because I'll need that as well. So square task. Square task will only be for one big integer, of course, because you don't need to square 2. So just have the big integer a, like that. And here I'm going to say, in compute, I'm going to say a dot square. And square is a function inside big integer, but it's not public, so we can't call it from the outside. But it figures out when we're doing a square, and it does it internally. So there's my square and my multiply. Now, if you go back to our other code, where we had this, I make my v0 task. I then say v0 task.fork. And I then, instead of doing the v0 multiply directly, I then do some other work. I do a second multiply. And before I do my third multiply, I join. And I say v0 equals v0 task.join. I still haven't got a clue how this algorithm actually works. I don't need to know. I just need to know how to parallelize it. And then I do the same thing for v1. Except this time I'm going to do v1 task and v1 task. And this is going to be da1 and db1. So that's going to be here, and I'll do another multiply. In fact, there are 5 multiplies. I'll just do it after the last multiply. I'm going to say v1 equals v1 task.join. There we go. So I've basically now parallelized the Tomb-Cook algorithm. This is GPL. So if you take a photograph, you need to put that in the license agreement. Okay. Next thing, we're going to look at the square Tomb-Cook. Square Tomb-Cook. And square Tomb-Cook is going to make a square task, very similar to what we did before. Square task v0 task equals new square task of 8 naught. And then this is going to be v0 task.fork. And before I do my third square, so after the second square, but before I do the third square, I'm going to say v0 equals v0 task.join. And then I do the same thing for v1. So I'm going to say a square task v1 task equals new square task of da1. And then I'm going to say v1 task.fork. And then I'm going to say v1 equals v1 task.join. Okay, now, did I make any mistakes? Anybody see? Because I often make mistakes when I do this, especially whilst I'm talking. It's hard to code and talk at the same time. And hopefully this works. And hopefully it's going to get us better performance. Let me just also run top. Oh, there's top running. Okay. You can see that the Java process is running hot. So you're running at like, not just 100%, but it's running at like all the cores, and it's gone. It's all finished. So basically, we've now utilized our cores fully. So that's great. That's fantastic. And the performance is hopefully going to be better. Performance here is 14 seconds. So that's not too bad. I mean, we started with 46. We've made it to parallelize it a bit, and now it's down to 14 seconds. So that's actually not too bad at all. And we managed to utilize our hardware fairly effectively as well. So that's also a good thing. So let's put this into our code up here. This is demo 3 and test. That's not too bad. And we also want to, of course, commit that. Demo 3. And now we look at demo 4. Yeah, I've mentioned this already. The fourth thing I want to show you is, in fact, let me show you something else before I do that. One more thing I want to show with demo 3. And that is, I want to measure how long it actually takes to do the multiplications. So we get some idea of what we're dealing with over here. And I'll do this. I'll say long time equals. Now, it would be sort of obvious to say system current time millis. But it's not a good idea. Why not? Any ideas why this is a bad idea here? Correct. It's a system call. It's going to be too expensive. So we're only going to care if n is actually quite big. So if n is bigger than 10,000, for example, then we're going to use system current time millis. Otherwise, we're just going to keep it at 0. Then we're going to say try, and finally, we're going to say time equals, if n is bigger than 10,000, then we're going to say system dot current time millis minus time, otherwise just keep it at 0. And then if time is bigger than, say, for example, 50 milliseconds, we're going to print out f of whatever n it is, took percentage percentage d, not n, percentage d, milliseconds, and percentage n, comma time. So we're going to see how long each of those took, if it's more than 50 milliseconds. Less than 50 milliseconds, we don't really care. Right? So for the 100 million, just have a look at the numbers and see if you notice anything about the numbers. Do you notice anything here? Yeah, so it's, first of all, there are two things. One thing is it's either 999 or 000, but that's only because I'm starting at 100 billion. If I started at some other random number, it wouldn't be exactly that. But the thing which is more important is that you're actually working out the same number several times. Right? So if you want to make this faster, you can make it faster by caching the previous results, but not working it out over and over again, but putting it into a hash map. So that's the demo. In fact, let me just commit this and say demo 3 with timing. And what we're going to do is we're going to do this now as demo 4, where we actually create a hash map. Now, it needs to be a concurrent hash map because multiple threads are going to be putting elements in and taking them out. We also need to be careful not to generate a memory leak. We want to not have a static map, rather create it on the create it within the method, and then never let it leak outside of the method. So no static maps. So a couple of things here. Now, the first thing we'll do is we'll make a new method. The new method is going to have in here a map from integer to big integer, cache, and I'll make it private. Now I'm going to construct a map of integer, oops, that was wrong, integer, comma, big integer, cache equals new concurrent hash map. You want that one. Cache.put 0, comma 0, and cache.put 1, comma 1, like so. And then we're going to say return fn, comma cache. So we basically return that. Now, the thing is that inside of f, I'm not actually using that f, I'm using another f. So a good trick that I use, or a trick that's a bit funny, but it does work well, is you just rename that method. And then you can spot all the places where you need to use the new method, right? So there it's comma cache, and there it's comma cache. There we go. And then we change it back to just being called f. So what I do is inside my f method, I need to change that a bit as well. I need to say up front, I'm going to say big integer result equals cache.get of n. And if result is null, then I'm going to work out the actual number over here, and I'm going to say, instead of saying return, I'm going to say result equals, and result equals, I'm going to put it into the cache. I'm going to say here cache.put n, comma result. And then I'm going to say return, outside of the if, return the result. So I'm going to basically do something called compute if absent. That's what I'm actually doing. You can't use compute if absent here. Any ideas why you can't use compute if absent? Why would compute if absent not work? Nobody knows. I'm not surprised. No, not because I've blocked threads. Not because of that. The reason why, no, it actually wouldn't actually run. It wouldn't run. And the reason is very obscure and not documented very well at all. That you're not allowed in the if you have a function that generates the value for computer absent, that function is not allowed to change the map at all. And if you do, bad things happen. With the normal hash map, it happens to work. Concurrent hash map, you get an infinite loop, live lock type of situation. So, and in Java 9, they now throw an exception when you do that. So they're specifically code against that. Okay, so as nice as computer absent looks on the outside, it's not usable for this. Let's run it and see how we do. Now, the total time hopefully is going to come down a bit, unless we've done something wrong. It has come down. So for 100 million, we're now doing it in 10 seconds. That's demo 4. You notice anything? It's still happening because of the nature of this particular algorithm, right? Because we're always dividing by 2, but we're dividing by 2 in 2 different directions. So there's still a possibility that this can happen, but we have actually saved like 30% of our. You have improved by 30% our performance. So that's not too bad at all. This is now demo 4. So we are getting better. And we're going to just do commit demo 4. Okay, so how do we get around that? Now, one way to do it is with our map to not just put the entry in, but to put a placeholder object into the map that sort of says a reservation of I'm going to work this out. So this is one way of doing it. I'll show you another way. I'll talk about another way a bit later. But this is one way where instead of putting the value in, I use a method called put_if_absent to put a special placeholder object into the map. If the result that comes back from put_if_absent is null, then we were the first, and we can immediately start doing the calculation. If it's something else, then it's the placeholder, and we wait until it's done. Now, I'm going to show you one of the simplest ways of doing it. You could do it a better way, but this is just a simple way. And it's unlikely the actual wait notifier is unlikely to be the bottleneck here. So we're not going to be the most efficient, but it will hopefully work. Okay, so here's what we do: is instead of saying calling get, we say put if absent in comma reserved. And reserved is going to be a constant, no, not a constant field. It's going to be a private final field equals value of -1,000. So it's going to be unique per Fibonacci object. So if you make multiple Fibonacci's, you're going to also have different reserved objects. And then we're going to, over here, say if result is null, that stays almost the same. So if the result is null, we were the first to actually successfully put reserved into the map. But if the result is equal to reserved, then we were not the first. Somebody else beat us to it. But they haven't finished doing the work yet, but they beat us to it. And now we're going to basically say while result equals cache.get n is equal to reserved, whilst it's still equal to reserved, we want to wait until it's ready. So I'm going to just use a very primitive mechanism here: synchronized, reserved, and over here I'm going to say reserved dot wait. So I'm going to wait until it's no longer equal to reserved. And then around this, I'm going to put a try catch interrupted exception, throw new cancellation exception interrupted, for example. Okay, so this will suspend the thread and wait until the job's done. So, and then once I've put it in, where I say cache.put, I'm going to wrap this with a synchronized, and I'm going to, after putting it into the cache, I'm going to say reserved dot notify all. So anybody who cares about this gets a notification to say, hey, something's changed. Now, it could happen that unrelated threads that are waiting for different numbers get woken up, but it's such a quick operation to sort of go back to sleep, it doesn't matter. And if it does matter, you'll see it inside your thread dump because you'll have lots of threads blocked on the monitors. But I think it's very unlikely that you'll see that. Let's run this again. And now, you should see every number only being calculated a single time. Right? I think that's clear. It's only, everyone's only, so if we look at 100 million, for example, there, everyone is only once. And we've improved our performance, of course. You work out less and you get better performance. So we got down from like 46 seconds with some caching and stuff down to 7 seconds. So that's a nice improvement. Let's put this in as well. This is now demo 5. And demo 5. Now, if you run, I'm going to run this once more. This I'm going to do some thread dumps whilst it's running. Okay. And what you'll notice is that at the beginning, if you look at the beginning of the run, there are. This is now the dump I took near the beginning. There's worker 7 and 6 and 5 are waiting. Worker 4 is working. Worker 3 is waiting. Worker 2 is waiting. Worker 1 is waiting. And the main thread is working. So it's basically like, was it two or three threads actually doing any work? In fact, 2 threads doing work, and the rest is sitting around waiting. Now, the fork join pool, the fork join pool concept is built for parallelism. It's not built for IO-based concurrency or for any blocking operations. So we don't really want to block when we're inside the fork join pool. Now there is this idea that you can optimize this by telling the fork join pool when you're about to start blocking, called the ManagedBlocker. And it's implemented by 2 classes at the moment in Java. The phaser, Java 7 phaser, which is a replacement for countdown latch and cyclic barrier. And the second one is completable future. That one also internally uses the ManagedBlocker. Let me show you how it works. Before I do that, did I commit that last bit? Yes, I did. Okay, good. So I committed that. So the next demo is to implement a ManagedBlocker so that when the threads when too many threads are blocked, the fork join pool is allowed to construct additional threads. You see, when you configure the fork join pool, you cannot specify the maximum number of threads. You can only specify what the desired parallelism level is. How many threads do you want to have work at the same time? That's the thing. And so that really is going to be pretty close to the number of hardware threads. In fact, the typical number for the desired parallelism for the common pool is number of hardware threads minus 1. So on my machine, I've got 8 hardware threads, so it says 7. And the reason why it's minus 1 is because the main thread is also working. Whichever thread does parallel streams or does fork join is also going to be doing calculations. So that's why it's minus 1. Okay. Now, what you can do is you can give hints to the fork join pool that you're going to start blocking now. You're probably going to block now. And it allows the fork join pool to construct additional threads to keep the parallelism high. So that's what this does. And it gets rid of the time at the beginning where you've got black, where you're not actually really parallel. Let's try and do that. It's very easy. All you need to do is to take this code here, this waiting code, and wrap it in a class. That's all we do in an interface. So we're going to here make a private class reserved, it's called a reserved blocker, implements ManagedBlocker, which lives inside fork join pool. It's got 2 methods, block and is releasable. And I always like writing is releasable first. Is releasable is going to basically be this this precondition over here, this conditional predicate over here. So this is what we call a conditional predicate. And it's going to be the reverse of that. So basically, return that the result is not equal to reserved. So we're going to call cache.get, and that shouldn't be reserved. Once it's not reserved, then it's releasable, and you can exit. Okay, so we need to create fields for this. So we're going to have a private big integer result. We're going to have the cache. Let's make a copy and paste of that because it's a bit too much typing. In fact, let's take both of these and make them fields. There we go. So private final int and private final cache. And we make a constructor for those and in cache. And then is releasable is basically done. So we're going to pass into this constructor the end that we're working on and the cache. And it's going to query the cache and say, is this still equal to reserved, yes or no? Once it's not equal to reserved, then we're good. It will never become null. Okay, but it could become, because we don't remove entries from there, but it could become the actual number. And then block is going to look very similar to this over here. It's going to be basically, say inside here, synchronized reserved whilst not is releasable, reserved.wait, and then once we're done, we say return true. Okay, return true. And now, the way you use it is inside here, we say try, we're going to say reserved blocker equals new reserved blocker, passing in the end and the cache. We're going to say fork join pool dot manage block of the blocker, and blocker result equals blocker dot results. So I get the result from the blocker. Now, because there's only one thread reading and writing that particular field result, we don't need to make it volatile. You can make it if you feel unsure about it, but it doesn't have to be in this case. Now, for 100 million, you won't see such a big difference. I'm just telling you because it can happen that it actually seems slower. But if you get to take a bigger number, like 250 million or 1 billion, then you will see quite a big difference. Because at the beginning, just nudge him there. Just nudge him. Thanks, yeah. At the beginning, there's quite a bit of black inside the run. So let's run this again. This is demo 6. And 100 million. And I'll show you some thread dumps in a moment that'll demonstrate this. 100 million completed in 6.9. Oof. The last two times I'd showed this, it was slower, so I was quite lucky this time. But it's very close with such a small data set. The problem is it doesn't really work if I'm showing you a demo that takes 10 minutes to run, so, where you can actually see the difference, right? But here we were lucky, it did actually come through a bit faster. Okay, so let's write that down. That's demo 6 using the managed blocker. And I want to also do one more thread dump here. If you... Oh, wait, I need to get some... Let's do that again. And thread dump. Thread dump. What you'll notice now is at the beginning, you're going to have a whole bunch of other threads, thread names besides 0 to 7. You've got like common pool worker 31. Of course, you don't want to have too much of this stuff going on because constructing a thread is a very, very, very expensive operation. It takes like a couple of microseconds to do, which for a computer is a very long time. For us, it's a microsecond is fast, but computer, it's actually quite slow. So But you'll see that it's before it was 7. Now it's actually up to 31. It could be all sorts of numbers. In total, there should be only 7 threads really working at a time, maximum. But you can improve your utilization of your cores. So that's a little basically most of my talk. I've added one more slide just for you guys, and homework for you, right? So you've seen how you do this with fork join pool and with ManagedBlocker. You can do something very similar with completable future. The 2 methods you need to use for that, one is then accept both async. Async is important, and complete. And together with those, you can actually go and you can implement the same algorithm that I've done, and it should perform quite similarly to what we got here. There's one little catch with completable future you need to be aware of, and that is what happens if you don't have any threads inside your common fork join pool. That's one catch, and the fork join pool is very peculiar. If I've got 8 hardware threads in this machine, so when I say we look at the common fork join pool and I say how many threads do you have, it tells me I've got 7 threads inside there. What do you think happens if I've got 2 cores, 2 hardware threads in my system? What would it say? 1, correct. Because 2 minus 1 is 1. What would it say if I only have a single core in my machine? No, it will say 1. And there will actually be a thread constructed that will be running inside the common fork join pool. So by default, there's always at least 1. Even if there are 0, and if there's only one core, it will have the main thread running plus the thread inside the fork join pool. Now, when I talk about this, people say to me, but who has single core machines nowadays? Quite a few, because of all the virtualized machines. They have single cores, maybe 2 cores. If you turn off the common fork join pool by saying parallelism equals 0, how many threads will be in the fork join pool? No, 0. But what will it say? It will say 1. Okay, and true. They will never tell you that it's 0, and the reason is, and you will probably not believe this, but it's true, they are so scared that we are so idiotic that we're going to get division by 0 errors if they ever tell us a 0. So instead of telling us the truth, they tell us 1, so in case we make a mistake. Now, this actually has an effect on completable future, but I won't tell you what it is. You've got to discover that yourself. So here's some homework for you to do, and if you go to my GitHub, it's in the PDF on the GitHub, and once you got the answer, send it to me on that link there, and we'll see who gets the best answer first. Thank you very much, and we've got time for 1 or 2 questions. We've got 2 minutes and 30 seconds left. It sort of tries to keep it at 7. So what it'll do is it'll, if it blocks a thread, it will. I think it stops them once the other, if it sees that another thread is taken over. So you're not going to have all of a sudden 100 threads running. You're going to have only 7. But whilst it's blocked, it will construct other threads to keep it happy. Yes, sir. Okay, so the question is, could we just put the recursive task into the cache? Yeah, you could do that. I've done that. But the problem is that you would then have to do a ManagedBlocker on the join. And that does get a bit tricky. No, the joining... So I have done that. For example, I've done it with future task. I put in a future task. But the problem that you always run into there is that if you want to prevent multiple from working out the same one, well, we put a future task in. But then you'd have to work out get You'd have to call get on the future task. And if it's not done yet, it has to wait for it to be completed. So you end up having to then, jump through hoops to try and do that. It's a bit difficult. Another question? I saw a question over here. Yes, sir.
Is there any way to limit the number of threads that you, when using ManagedBlocker, that you can get out of the join pool?
Okay, so the question is there any way to limit how many threads will be constructed in total within the fork join pool? And I don't think there is. There is sort of a safety within parallel streams, but even that's not completely fail-safe, because if you've got a good split iterator that splits down the middle, always down the middle, then it's not going to construct more threads at the same time than number of threads times 4 inside the fork join pool. But if you have a very skewed split iterator, it could be more. You can end up with out-of-memory errors on this with the ManagedBlocker. But you can also get out-of-memory errors just with the normal fork join pool if you fork too many times before you join. That's why in my algorithm, and when I was parallelizing the big integer, I was always joining before I did another fork to help the fork join pool to keep the numbers at 7. If you don't do that, you'd end up with far more threads at the same time. One more question and then we're done. Yes, sir.
Have you done any comparisons, perhaps doing this with the coroutine framework? Avoiding creating new threads?
With which framework?
Like Kotlin coroutines or something?
Oh, no. So the questions have a compared it with Kotlin coroutines. I haven't. But do you know how they work?
Yes.
So your homework is going to not be completed with Future. It's doing this with Kotlin coroutines. It's very interesting to see the result, actually. Please send it to me. I'd love to see it. So thank you very much. I'll be here for the rest of today. Tomorrow I'm gone. So if you want to speak to me, more than welcome to. Thank you very much.